This is my Lab 5 presentation. The main purpose of this lab was to see how induced magnetic fields work. The main models and principles used were the Biot-Savart law, the on-axis magnetic field, the Faraday's law, and the results from the experiment were that the average time during the real-world experiment was 1.5 seconds, and the computed time was 1.719 seconds. The main values in this experiment was that the magnetic dipole moment was 2.09, the average time was 1.5 seconds, the computed time was 1.719 seconds, the length of the tube was 0.31 meters, the width of the tube was 0.004 meters, the inner radius was 0.02 meters, and the mass of the magnet was 0.025 kilograms. The main physics idea in this lab was Faraday's law and induced magnetic fields. The system for this experiment was the bar magnet, the earth, and the aluminum tube. The surroundings for this experiment was everything around the aluminum tube. Some potential errors were that the timing on the magnet dropping was not precise, the tube was not held perfectly vertical, and some assumptions were that the bar magnet had the same dipole moment that was calculated in Lab 3. This slide shows the glow script model and the velocity versus time graph. At the start and end of the tube, the magnet has an acceleration because its velocity is changing, but during the middle of the tube, there are equal and opposite forces acting on it, and the velocity is constant. And the blue is a clockwise current, while the red is a counterclockwise current. This is because the red current provides the induced magnetic field on the magnet. So the dynamics of the simulation would not change if the magnet was flipped around. The total time in tube of the real-world system was shorter than the computational system. The computational system could be more accurate because it does not consider the human errors that can happen in the real-world system. The shape of the velocity versus time plot shows that there were unequal forces acting on the magnet at the beginning and end of the tube, since there was an acceleration on the magnet. And when the magnet was in the middle of the tube, there were equal and opposite forces acting on the magnet, since there was a constant velocity. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The induced current in the conductor would be much larger. This would cause an even greater induced magnetic force on the magnet, resulting in the magnet falling more slowly through the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would reduce the ring currents in the tube, which would mean less of an induced magnetic force on the magnet. This would mean that the magnet would fall faster through the tube.